Welcome to note set 12, and actually we're going to make this part A. This is a fairly large note set, so to make the video size a little more manageable for me to upload and so forth, I'm going to split it into two. I'm not going to change the note set on the web page. I'll just have two different videos, part A and part B. So we're going to talk about some discrete time filters. A lot of this, some of this will be kind of stretching review, and a lot of this will be some new ideas. So hopefully this will get you excited and moving into some things that are very, very brand new from what you've seen before. So we are in section 5.4 of Proachus and Monolachus. And I follow it pretty closely, unlike on some of the previous note sets where I had my own agenda, so to speak. Okay, so let's move on here. So before we get too far into this, we've alluded to this ideal filter idea, and we did talk about this in Signals and Systems, but let's nail this down here. So we'll talk about this for a low-pass filter. But these ideas can be generalized to ideal high pass and ideal band pass and ideal band stop and things like that. But so for the low pass idea, what we want to imagine is that we've got some desired signal x of n that lies in some range of low frequencies, completely lies there. So in other words, we're saying that its DTFT is 0 at frequencies from omega 0 to pi, and then from a minus omega 0 down to minus pi. So we get that by talking about the absolute value. So we're basically saying at high frequencies, this desired signal has a DTFT that's completely 0. So, but even though we're not talking about it here, presumably there is some undesired signal that lies in those frequencies where the desired signal is 0. So we'd like to pass the signal through the filter and keep these desired frequencies, but get rid of the higher frequencies where there's presumably some interference or some noise. So that would be the ideal setup where the undesired stuff is in a band outside of the band where the desired signal lies. So obviously we want the filter to be 0 in the range where the undesired filter is. So in this range we want the filter to be 0. But where the signal is non-zero, the desired signal is non-zero, we want the filter to be basically flat. And if we think about it, what we want to come out is that if we put in only the desired signal, we'd like the desired signal to come out pretty much untouched. And what we're going to allow to happen is we're not going to allow the shape of the signal to change at all. We're going to allow it to get a little bit bigger or smaller. That's fine. We can always change that by multiplying it by an appropriate 1 over capital C. So we'll allow that to happen. And then the other thing that we'll allow to happen is that it comes out delayed. And that kind of makes sense. We see this idea of a block diagram with these delays, and we recognize that it takes time for the signal to kind of propagate its way through these delay boxes. So even if we're setting up our system so that it doesn't change the shape of the signal, it's going to take some time for it to propagate through. So that's why we allow a little bit of a delay. And we try to keep that small. And the reason that we try to keep it small is, obviously we don't want it to be hours. So we might be able to accept, depending upon the application, milliseconds or maybe even a second or two, depending upon what it is that we're trying to do. So if we look at this, if we take this equation and we take the dTft of it, on the left side we get yf of omega. On the right side, well, by linearity we get a c out in front, which we haven't really drawn out in front. Then we get an x n minus n0 in the time domain. Well, by the time shift property, that's just going to be x of omega times an e to the minus j omega, and that should really be n0 instead of t sub d. So that's what we get here, and that comes just completely from applying the time shift idea to this desired output of the signal being just a delayed and amplitude scaled version of the input. So if we look at this, we have this set up so that our output is equal to the input dTft times something, and so that has to be our desired frequency response. Now remember, we want that only over the range where the input signal is non-zero. So we want that out to omega 0, but then you know, from omega 0 up to pi, we'd like the magnitude to be constant. So we can specify this here. So for omega in the passband of the filter, so from minus omega 0 up to omega 0, we want the magnitude of this to just be equal to c, and we want the angle or the phase of this frequency response would just be the phase of this thing, and taking that c is greater than 0, the angle of c is 0, so we just have the angle of this, which is just minus omega n0. So the phase of the filter is just a line as a function of omega with a 0 intercept and a slope of minus n0. So the amount of delay that we get or that we're allowing sets the slope of this linear phase. And that's a very fundamental result. So here's what we've established. And again, I've missed that t sub d should be n0. So what we've got here is an ideal low-pass filter that is constant, and we can usually take that as 1 if we want to, out to omega 0 and down to minus omega 0, and is 0 elsewhere. And then in the passband, our phase is just a straight line. And so this is what's known as a linear phase filter. So it's a constant magnitude linear phase filter in the desired passband, and identically 0 outside of the desired passband. So this setup is what we would consider to be an ideal low-pass filter. So just summarizing this idea, our magnitude response is constant in the passband, perfectly 0 in the stop band, and there's no what we would call a transition band between the passband and the stop band. It just goes instantly from passband to stop band. Later, when we design real filters, we'll see that it's useful to have a transition band between those two. Our phase response, on the other hand, is linear in the passband, and the slope of the phase is the negative of the delay, and it's undefined in the stop band. I mean, if we have something that is 0, so the complex number 0, what is its angle? Well, 0 e to the j, anything is still 0, so that's what we're saying over here. So the phase is really undefined. So that's our definition of an ideal low-pass filter. And to be honest, even though these things don't exist, as we'll see in just a minute, when we're thinking about at the high level of how to do some signal processing task, we often work it out just thinking it through thinking, okay, imagine I have an ideal low-pass filter. How would this work? So if you can't get things to work, theoretically, imagining that you have access to an ideal filter, you'll never get it to work in the real world. So you often think things through in terms of ideal low-pass filter, and then you go back and say, all right, what do I really need to make this happen? That I can actually. So it's important to remember that the frequency response is a DTFT. It's the DTFT of the impulse response. So this frequency response is periodic. So we really only need to look from minus pi to pi. So here's our beloved minus pi to pi range. And we see that we get periodic replicas spaced every 2 pi. You don't often draw all those things, but you certainly should be aware that they are there. So that's all I'm trying to show on this slide, is that you should keep in mind that that all those replicas are there. And of course, the signal that's applied to the system, it has a DTFT, and it's replicated in all those places too. So you basically have, it's like walking into a one of those fun house mirrored rooms in a fun house, and you suddenly see 5, 6, 7, infinite number of you all doing the same thing side by side. That's kind of what's going on here. So it's kind of the funhouse mirror room of the DTFT, so to speak. Okay, I think we should leave that analogy where it is. So I've been alluding to the fact that these ideal filters can't exist in practice because they're non-causal, and we can easily see that. We'll show that for the low-pass filter case, but it's easy to show it for any of the other cases: ideal, high pass, band pass, whatever. If it's ideal, meaning that it's perfectly flat in the pass band, it's perfectly zero in the stop band, no transition band, then we simply cannot actually build it. So here's our frequency response. Again, I've carried through my, at least I'm consistent, carried through my, well, I'm not consistent because I have N0 there. So, if that's our frequency response here, if we take the inverse DTFT of this rectangle and work it with the time shift property, we can end up getting something that shows that the impulse response looks like this. So it's a sinc function. There's the effect of the linear phase causing a delay of N0 on the sinc function. So if we look at what this means, we put in a delta function that happens at n equal to 0, and the response of the filter starts before it even sees that. So the question that you ask is, how does a real-world filter know that this is going to happen at n equal to 0 so that it should start doing this, in fact, all the way back at time equal to minus infinity? And I made another typo here. That should be our N0 as well. So clearly this is a non-causal filter. There's no way that a filter can anticipate that the delta function is coming and start at time equal to minus infinity, doing what it should do based upon something that will happen infinitely far in the future. So it just simply cannot happen. So we cannot build such an ideal filter. Okay, so given that, we still can draw nice ideal filters for all the different types. Like I said, it's often convenient to first work out your high-level ideas using ideal filters as your prototype, and then refine your design to work properly with filters that you really can design and actually build. So here are a bunch of different filters. all shown as ideal filters. We've got the low pass, which we've already talked about, and notice that we're only showing them in the minus pi to pi. They repeat periodically outside, so I would encourage you to think about what these things will look like. So you might want to stop the video right now, try to visualize or sketch what these things would look like extended out, because I am, spoiler alert, going to sketch some of these on here. So stop the video, give it a shot, and then turn it back on and see. Well, we've already looked at what the low pass looks like extended. The high pass extended would look like this and this, and then go to 0, and then out at so that's centered at pi. Out at 3 pi, we'd get another one, and so on and so on. So that's really the only one that I'm going to show. The others I think you can work out. So we get a band pass where we have omega 1 and omega 2 setting the edges, and the pass band width we would specify as B. That's the omega 2 minus omega 1. Then we have a band stop where there might be some band of frequencies that we don't want to go through, that's kind of in the middle of the 0 to pi range, and so we eliminate those. And then we have this curious one down at the bottom, the all pass. Now looking at it from a magnitude response, you'd say, why on earth would you want to use that? It passes everything. Well, that's from the magnitude point of view. These are actually often used to adjust the phase of some of your signal as it passes through. And it might be done to adjust the phase, to undo the phase that was imparted on your signal by some previous filter. So in some sort of phase equalizer in some sense. Okay, so those are the various types of filters, and there are some other ones, but those are the main ones that you'll encounter. So I alluded to this earlier with a little bit of feed-forward topic, talking about how to design a filter just by putting poles and zeros where you think you need them. So we'll talk about that a little bit more. But later on, we will get to some very high-powered methods for filter design where you don't really need to try to guess where to put poles and zeros. But for right now, let's just think about this idea for now. I can't do that for some reason. I'll try to get rid of that. All right. So here's our standard transfer function. We've got the numerator and the denominator spec'd as we would get it directly from the difference equation. We've got it in the z inverse form here. And we can imagine factoring both numerator and denominator. Even though it's in terms of z inverse, you can still factor it just like a regular old polynomial. And so we would factor it into these forms. And you can see that the p sub k and the z sub k set the locations of the poles and zeros. The p sub k's set the poles, and the z sub k's set the locations of the zeros. And so if we just start throwing down some poles and zeros, here are 3 different low-pass filters. Basically, for a low-pass filter, we want to put poles near omega equal to 0. And remember, omega equal to 0 is right here on our unit circle. So it's at the position z equal to 1, because z equal to 1 is e to the j 0. And where the 0 is the omega, because remember, on the unit circle, z is equal to e to the j omega, where that omega plays the role of the discrete time frequency. Okay, so we've got these 3, not the only types of low-pass filters, but 3 low-pass filters that that we've just wished into existence by just tossing down some poles and zeros. So we've got a first order, we've got a second order, and a third order, the order being set by the number of poles that we have. As we go to the higher orders, we have more poles to kind of carefully place in this region to carefully craft the passband structure. And then, as we go to higher orders, we have access to more and more zeros as well, because the number of zeros is usually no more than the number of poles. And so we end up getting, the possibility of tossing a zero over here. We could have done that for the second order as well, but we didn't. Sorry, there I yawned a little bit there. It's a little bit late at night while I'm making this. I'm trying to get ahead of the curve on making my videos, so I apologize for that. So those are just three possibilities. A lot of other possibilities as well. Those are just three. So let's look at the ones below that, which are Highpass. And there we want to be putting poles over here in the region of plus or minus pi, omega equal to plus or minus pi. And so that corresponds to the z equal to -1 position. Now, we'll be coming up in just a bit talking about some ideas of how to transform a low-pass design into a high-pass design. And so to set the stage for that, if we just take a look at these, let's just look at these. Whoops. Okay, that caught me off guard. Okay, I got to set my pen here. If we look at just these two, we can see that what we've really done is it looks like all we've done is flipped it around this vertical axis. But to make things a little bit easier to think about, let's imagine that instead of doing that, what we've done is flipped it instead, flip both around this axis and this axis. And because we have symmetry along this arrow, so we have symmetry across the horizontal axis, flipping it on that horizontal axis doesn't really do anything, but it will make the mathematics of doing this easier, that we'll do later. So just what that means is that we're negating the real part that flips it in this way, and we're negating the imaginary part that flips it this way. And if we're negating the real part of z and we're negating the imaginary part of z, that means we're just negating z in and of itself. So we'll leave it at that for now, just alluding to this idea that once we have a low-pass design, we can transform it into a high-pass design by just everywhere there's a z, replacing that z by -z, and we will automatically transform low-pass into high-pass. And no surprise, if we started with a high-pass and we replaced the z in that by -z, we would transform it into a low-pass. So that's a low-pass to high-pass transformation, and we'll talk more about that in just we've seen this slide already, just thought it would be a good idea to revisit it. So just, I'm not going to spend a lot of time on this, but, given what we've been talking about, you should, revisit this. Also think about this idea that putting a pole or a zero at the origin does nothing to the magnitude. It only changes the phase. And I'll leave that for you to puzzle out why that would work. But I will say that suppose we start with an h of z. If we want to put a 0 at the origin, we would modify h of z by multiplying it by z. That'll put a 0 at the origin. If we want to put a pole at the origin, we would multiply h of z by z to the minus 1. So take a look at both of those, convert it into the frequency response form, take the magnitude, and you'll see that the structure of that out in front just kind of goes away. It has no impact on the magnitude. It does impact the phase, though. So I'll leave that as an exercise for you. Don't you just love that when books and professors say that? Oh well, we do it for your own good. Don't you love that too? Sounds like a parent talking to a child, right? Okay, moving on. Let's take a look at some simple low-pass filters. We'll just look at two cases. And again, these are by no means great filters, just trying to illustrate this idea of playing around with poles and zeros and what effect those things have, just to get a feeling. So it's like you've moved into a new neighborhood. You're going to go out and walk around and check out, where's the cafe, where's the bar, where's the grocery store, where's whatever, where's the playground, how far away is this, where does that street go, what happens if I take this street instead of that street. But simple things. You're not going to go very far. You're just going to stay right in your little neighborhood. So that's the kind of thing that we're looking at here. Some very simple low-pass filters. And so here we've got one where we've got a pole on the positive real z axis, and we've got a 0 at the origin, and that would correspond to a transfer function that looks like that. Why do we have that 1 minus a up in the numerator? Well, 1 minus a is just a number, so it's not really it doesn't have any z involved with it. And where are we getting that z at the origin? Well, remember, this is in the z inverse form, and it's easiest to see poles and zeros in the z form. So multiply top and bottom by z, and you'll get some constant, 1 minus a times z. There's the 0 at the origin. And in the denominator, you'll have z minus a, and so you'll see that a, if it's that a should be a positive number, so like z minus 0.5, we'll put this at halfway between the origin and the unit circle on the real z axis, positive real z axis. Okay, so if we use MATLAB to plot the frequency response of this thing, I've done it here for an a equal to 0.9, so I'm putting the pole pretty close to the unit circle, and you can see that at omega equal to 0, I get a height of 1. So my so-called DC gain, remember omega equal to 0 corresponds to DC, direct current, constant signal. And so how did I get that? Well, notice that omega equal to 0 is z equal to 1. So if I plug z equal to 1 here, that goes, that z inverse just becomes 1, and I get 1 minus a over 1 minus a, which is 1. And so that's why I have a height of 1 there. And that's why I have this 1 minus a up there, up at the top. All right, let me get rid of a bunch of this stuff here, and then we'll move on here. So that's that one, and we don't have anything out here tacking it down. There's nothing on the unit circle tacking it down anywhere, so you can see that we never go down and touch 0. Remember, our air hockey table is blowing the surface up and keeping it from hitting the ground. Okay, what if we do want it to go down to 0 a little bit more? Well, we can take our 1, 0 there and move it out here. And I don't know how that dark cross got there, but I must have done something funky in PowerPoint, and when it converted over into PDF, it showed up dark. I don't quite know why. But so we want a 0. I did that again. We want a 0 at z equal to minus 1, so this term will give us that 0. And again, it might be easier for you to multiply top and bottom by z. Then you see that the numerator is z plus 1 and the denominator is z minus a. So you can see how we get that 0 and that pole. And so now if we compute this, then we see that we get this curve that comes right down and goes to 0 at omega equal to plus and minus pi. And down here we have at least a portion of the MATLAB code to create these plots. It's not it's not doing all the labeling and all that and the actual plotting, but it's showing you how to generate the freq z, at least for case number 1. I'll leave it to you to see if you can puzzle out how you would do case number 2. Okay, so that's that case. Let's look at simple high-pass filters. As I stated before, we can convert a low pass into a high pass by taking z and replacing it by negative z. So if we start with our case number 2 low pass filter, so the H2 of z, and we replace z by negative z and assign it to the name H sub 3 of z, this will give us a high pass filter. So you can see that we had a plus z inverse there, and we now have a negative z inverse. And we had a negative az inverse there, and we now have a plus az inverse here. So that's just simply everywhere there's a z, replacing it by negative z. And so what that does is it flips the pole zero diagram along the horizontal axis as well as along the vertical axis, although no real action flipping along the horizontal axis because everything was on the real axis to begin with. But nonetheless, technically it is flipping along both of those axes. So here's our new pole zero diagram, and we can see that we have a 0 at z equal to 1, which corresponds to omega equal to 0. So we could have predicted that kind of shape. And we've got a pole out here at plus and minus pi that's pushing things up. So this looks just like what we had for the low pass, except now it's shifted into a high pass form. So that's nice. Let's present here to the next slide. We can do the same kind of thing here for simple bandpass filters. So if we put poles at some complex location at a radius r from the origin, and here we're just picking to put them at pi over 2. We could have put them somewhere else, but this is putting our pass band kind of smack dab in the middle of our 0 to pi, but we could put it somewhere else. So if we work all this out, and we're also going to put a 0 here and a 0 here, so the first 0 gives us that behavior, and the 0 over here gives us the behavior at plus and minus pi. So we're tacking down the response outside of the pass band, the narrow bandpass pass band. So that's good. That's desirable. So those zeros come from here, so we can puzzle those out. The z minus 1 gives us this one, and the z plus 1 gives us the one at z equal to negative 1, which gives us the plus and minus pi. So we've got that taken care of. Let me get rid of this here. I'm getting pretty good at taking care of those things, and I even remember to go back to my pen so I don't start moving the slide all over. Now to get these things, for this case, since we're at e to the plus or minus j pi over 2, remember e to the j pi over 2 is equal to j. E to the minus j pi over 2 is equal to negative j. So that's how we got these two results. So we can write the denominator as z minus jr times z plus jr, and if we FOIL that out, if you remember FOIL from high school maybe or early college, stood for first, outside, inside, last. So we're just doing the product of that. You'll see a bunch of things cancel, all the imaginary parts cancel, and we're left with z squared plus r squared in the denominator. So that gives us these two poles, and those will correspond to the resonant peaks. And we get some crazy wild phase response that's certainly not linear, so this is by no means ideal in magnitude, nor is it ideal by phase. But it gives us a nice, simple bandpass filter that could be very usable. One could argue that near the passband, things are actually fairly linear in phase. So this might not be that bad of a design. Okay, so very simple design of a passband, of a bandpass there. I want to talk a little bit more about this low pass filter to high pass filter transformation. We saw graphically the idea of moving poles and zeros by replacing z by minus z, and that flips the pole zero diagram around the horizontal axis as well as around the vertical axis. But let's look at it from another point of view and see how we get there. So here we have, and we'll illustrate this with an ideal low-pass filter, just because it's easy to draw, but it captures all the ideas that we really want to show. So we'll just leave it at that. So we'll illustrate this with a nice low-pass, ideal low-pass filter. So here's a structure for our magnitude response for a nice ideal low-pass filter. And remember, it's periodic. So we could shift this whole thing to the right and move this over to here, move this over to here, this gets moved over to here, this gets moved to here, this gets moved to there, even though I'm not showing it. So we've got a bunch of stuff there that just gets moved over. And so when we do that, we see that we end up with something that looks like a high-pass filter. So here is the passband on the positive frequencies. Here's the passband on the negative frequencies. And here's our beloved minus pi to pi range. And so this stuff here is outside of our minus pi to pi range. That's just part of the replica. So everything's good. So it all makes sense. And so we can see that in addition to doing the z gets replaced by minus z, in the z domain for the transfer function, from the frequency response point of view, transforming low pass into high pass is just a matter of shifting to the right by pi. In fact, I mean, we could shift to the left too. Same thing would happen. But we're going to shift to the right by pi. So we can say that a general transformation, if I've got any low-pass filter and I know what its frequency response is, I just go in and I replace omega everywhere by omega minus pi, and that will give me the frequency response for a high-pass filter that will have the same shape as the low-pass filter, just moved to an appropriate position. So that's pretty straightforward and a really nice help. But let's see how we actually do it and where it leads us. How, if I said, here's a filter and I've got some hardware for it, or I've got some code written for it, and it's a low-pass filter, and remember, we don't implement using the frequency response. We implement using convolution, or we implement using the difference equation. So what would we do? How would we modify that code or hardware to get the high-pass filter? Well, let's take a look. So the frequency response to the low-pass filter is given by this. And so I'm using the sub LP here to indicate that. And here's my high-pass filter. just by notation. So I've got a sub HP, and I'm going to set that equal to my original sub LP with omega replaced by omega minus pi. So everywhere there's an omega here, I'm just going to replace it by omega minus pi. So that's all I've done there. Okay, so good. We've got that. And so now what? Well, so the next thing that we're going to do is look at what happens as we go to the next line down. We're going to look at this quantity here and notice that we can break that into e to the minus j omega k times e to the plus j pi k. So here's what that factors into. So if you're rusty on your exponential properties, you need to brush up on those because those are crucial. So we just split it using properties of exponentials, and then we go, okay, well, e to the j pi k, so let me write that down here, e to the j pi k, here's another property of exponentials, is equal to e to the j pi raised to the k. And what is e to the j pi? Well, that's just -1, and so e to the j pi k can be rewritten as -1 to the k. And so that's where I get this quantity here. So let me just clear this off a little bit here. And so when we do that, we can now group that -1 to the k with the original coefficient. We can group the -1 to the k down here with the original a coefficients, and we have the new high-pass filter coefficients. So we take the BKs and the AKs, and we just alternate their signs following this rule. So that's very easy. So you give me hardware or software that have has a difference equation built into it. From this idea, I can trace this right back to my difference equation. All I have to do is go through and negate every other coefficient in my difference equation setup, and I will convert from a low pass to a high pass, and vice versa. As we said, high pass gets, if I start with a high pass, the same process takes me to a low pass. So that's a really cool idea, and it works really well. So let's keep going. Idea. We change our focus to the transfer function. We're going to now mathematically prove that our idea of flipping along the both horizontal and vertical axes gives us what we want, and that corresponds to just replacing z by -z. So here's our low pass filter. We can immediately write down what the z transform for our high pass filter was. We keep this structure, and we're just replacing the exponentials, the e to the j things, by z's, by the appropriate z's. And then we're just going to, let me back up a little bit here. Instead of grouping this with the b's and the a's, we're going to group those together. We're going to group those together, and we see that we get -z to the minus k rather than z to the minus k. And so we have proved that our result that we puzzled out earlier actually holds from a mathematical point of view as well. So illustrating what to do on the pole zero plot. So here's a pole zero plot for our low pass filter. I've got a pole here to push things up near the low frequencies. I've got 3 zeros stacked out there to tack things down at the high frequencies to give me my stop band. And let's look at what this replacing z by -z does. As I said, it flips across both of the axes, so you can see that these arrows take us across diagonally. Same thing with the blue ones. And then this 1, 0 that's on the real axis just goes over to there. And we end up with this structure. So we now have this very elegant way. You give me a nice low-pass filter design, and I can transform it into a nice high-pass filter design. And I can visualize it through frequency response, through transfer function, through pole zero plot, through difference equation, and well, here is the view of the difference equation. So we had the AKs get transformed, the BKs get transformed. So we're just alternating the signs, just like we predicted. And then finally, we can see the impact that it has on the impulse response. So if we did happen to have an FIR filter, and we were implementing it using hi, puppy. My dog just came up again to say hi. If we had an FIR filter and we were implementing it with convolution, we would need to know the impact of this transformation on the impulse response. So we can start from this result, which we already had, and see what impact that has. Well, a frequency shift in the DTFT domain corresponds to modulation or multiplication by a complex sinusoid of frequency pi in this case. So that means we're going to multiply our low pass impulse response by e to the j pi n. But e to the j pi n, we've been down that road already. It's just minus 1 to the n. So to change the impulse response from a low pass filter impulse response to a high pass filter impulse response, we just change every other impulse response sample in sign. That's it. Okay, so we've got one slide here before we break for part A of this set of notes, and then we'll come back and do a part B for this to cover the rest of them. So this just summarizes everything that we've seen here, so I'm not going to spend a lot of time on it, but it's kind of a one-stop shop for all these results for low-pass filter to high-pass filter. And remember, it works the same going from high-pass back to low-pass. So that's kind of nice. So we'll stop there, and I'll see you in part B of this set of notes.